Who were your mentors?
Oh, very important mentors. The most important were McCulloch and Pitts. These are the people that defined the formal neuron. That McCulloch was a neurophysiologist, Pitts was a mathematician. The formal neuron was a very simple model of the neuron in our brain. And they proved a number of theorems, including the fact that you could build a computer out of these formal neurons, which was not known at the time. Another thing that was not known at the time, they pointed out that the formal neuron had to have both excitation and inhibition in order for the circuit to work properly. The neurophysiologist at the time, this was 1943, said, no, there's no inhibition. We have not ever seen inhibition in the brain at that time. And McCulloch and Pitts said, there must be inhibition. We can give you this proof that without it, the circuit cannot work. And so this was one example of a wonderful prediction. Then later, of course, the neurophysiologists did find inhibition in the brain.
And where was this?
They were in Chicago at the time.
Where were you? That was where you were studying.
That's where. No, they were in Chicago, and then from there they went to MIT, and that's where I introduced myself to McCulloch when I was a junior in college, and that was the greatest thing you could imagine.
How did they affect you?
Well, for one thing, I mean, I'm very obligated to them. I had always been interested in the brain. And in fact, I'll be talking about consciousness because that is part of it. And among other things, the kind of mathematics I learned, and then the thesis advisor I had. Marvin Minsky was my thesis advisor. He's one of the founders of artificial intelligence. And Hartley Rogers, who did comparable sorts of mathematics, very called recursion theory. Nowadays would be called computability theory. So basically, they affected me because I was interested in understanding the brain, and they helped me go where I could go. They also pointed out to me, since I was interested in consciousness, that there's no way that we can look at consciousness. Why not? I really want to understand consciousness. He said, so Walter Pitts would tell me, well, you know, you have this thick amount of skull between the brain and you, and the only way we can see what's going on is using EEGs. There were other ways, you know, when people are on the operating table, they could do a little something with them, but basically you could not use EEG to find out very much. And so it was just not possible to do the science necessary to try to understand consciousness. And one of the things I'll be pointing out in my talk today is that, in fact, until 1989, when fMRI was finally made into a device that you could use to look into the brain to see how the brain is functioning, until that time, it was really not possible to have a science that explains consciousness. So my talk will be, although I worked in the neurophysiology lab, I am not a neurophysiologist. I'm a mathematician, computer scientist, electrical engineer. My talk will be about a model for consciousness. The computer scientists have a model called the Turing machine, well-known model, and it's the basis for a lot of the theory of computation. And so I have a model which I'll announce for the first time in today's talk, which I call the conscious Turing machine. And as a machine, it cannot do more than any current machine, but it's the architecture of this machine, which I will explain, that gives a machine the consciousness and the possibility of consciousness, and I will hopefully explain to people the architecture and also how it it brings about consciousness. I'm very excited about it because I never understood how you could even tell, how you could understand consciousness. I mean, after all, I'm conscious. I know I'm conscious. I know you're conscious because I know you're built more or less the way I am. But I don't know, how can I tell if a dog is conscious, or a cow, or a fish? You know, I had no tools for deciding that. And with this model of the conscious Turing machine, which is based on what these wonderful neurophysiologists have discovered and the suggestions they have made, they have essentially suggested how to understand consciousness. And I'm just amazed that they could do this. I mean, I have this model. It'll be a mathematical model, and I can use it. It's a very simple model, a very simple brain, but sufficient to be able to explain consciousness. And I'm just amazed that the neurophysiologists could come up with their understanding, because I had no idea even how to begin to understand it. And I guess most of the talk will be about a particular neuroscientist. They call themselves neuroscientists, and now there are many. His name is Bernard Bars. I love his model. There are many other people who have really very competent neuroscientists who have made great discoveries, ending with a person named Luigi Tononi, who, a very Italian name, and who...
Oh, go ahead.
So Luigi Tononi, who really has a way of not only explaining consciousness, but really giving a measure of how conscious the animal or the machine is. It's a way of measuring it, and this man, Tononi, really knows his information theory.
It's interesting that you have the intersection between math and neuroscience, which I imagine in the 40s and 50s. Well, this was in the 50s, was it?
So let's see, I was class of 59 at MIT, so I met McCulloch in 58.
Okay. And I do want to move on. Let's talk about actually the period around then, like between the time you met them in your junior year and let's say 5 years later. What changed in those 5 years?
Let's see.
So 50, what would that be, 58 to 63 or so?
That's the beginnings of artificial intelligence. Marvin Minsky was very much a mathematician. He wrote a book on the circuits of these included Turing machines, finite automata. It described how they work. It was a beautiful book. It was a mathematical book. And he wanted really to have AI. People were not building robots. And he had tried, he had in his own home all kinds of machines that he himself had built, but finally he got a graduate student who built a robot hand that's by hand, and this thing would come down on the table, bam, bam, until finally it got something and would grab it and put it over in the box. And then, you know, it just kept on doing this. I guess there was no eye, it was just this hand hoping to find something, and then so that was the very beginning of AI.
And what was happening in your life? I mean, how did you change in those 5 years?
Well, first of all, as an undergraduate, I was an undergraduate in electrical engineering, in part because I was actually hoping to be able to build robots myself. But I guess at some point I decided that the kind of mathematics that appealed to me and that I thought could best explain how be a good mathematics for understanding consciousness was something called recursion theory, which is the stuff that Hartley Rogers did and Marvin Minsky, both of them. That's the kind of mathematics they did. And so what changed is that I really got into that. I was an electrical engineer. I didn't know much mathematics. I took some math courses. I remember the dean, who happened to be my advisor, saying, "If you're taking math courses, no, you need to take these electrical engineering courses instead." But of course, like any other student, I went my own way. And
so recursion theory became computability theory, became complexity theory?
Yeah, recursion theory is computability theory. It was called recursion theory. It could have been called computability theory. It was logic and the kind of stuff out of which modern theoretical computer science came. I mean, the difference is that at that time, the logicians and the recursion theorists, the complexity theorists, were talking about Turing machines and what they could or could not compute, what was computable. And what made the big difference was the work of people like Steve Cook and Dick Karp, who really got a hold of not what is computable, but what is computable efficiently.
And that led to complexity theory.
And that is complexity theory, that's right.
So let's talk about the young researchers today, because of course they're all here for the first time. They have their own mentors, but then they're surrounded by all of these, the Turing and Fields and Abel Prize winners and so on. Have you been to the Laureate Forum before?
Yeah, I've been to all but one.
Really? I think that...
All but the last one.
That was the only other one I was at, so we missed each other.
So we did.
Since you've been here before, tell me sort of about the experience you have of mentoring these people, the ones who come to these forums. What do you see in them, I guess?
Well, they are certainly excited to be here. They bring energy, which is just wonderful. I was talking to a colleague, Professor Kahan, who I was here yesterday. I didn't see him at all. Why? Because he was surrounded by these young people. We just couldn't get to see him. And he takes his job very seriously. He really talks to them and is very inspiring.
Now, since you've been to all of them except one, you were at the first one 5 years ago. How do you think the forum has changed?
Why don't I tell you how I think it hasn't changed?
Please, yes. Frame it how you like.
How it hasn't changed. So, first of all, I do think this forum is amazing. It's wonderful. I met Klaus Tschira, and a formidable person. I really liked him as a human being, as well as the fact that he's wealthy and putting his money to very good use. So this was terrific. I really appreciated that. But there is one problem that my wife, Lenore Blum, pointed out. Lenore has been very interested in getting women into computer science. At Carnegie Mellon, where I'm a professor, we were very proud of the fact that 50% of our undergraduate computer scientists are women. 49.7%, she says. In all other universities in the States, it's 15%. So we have 50%, the others have 15%. And actually, if you want to find out how she does it, you'd have to interview her. But she has very definite idea, which she says is not rocket science, for what needs to be done for women to get comfortable and become scientists like everyone else. She does not believe that you need a special curriculum. She does not change the curriculum, and she just makes sure that women have the same what would you call it? The opportunities. that the guys have. So I'll just mention one thing. For example, a guy who's working on a problem can ask, and having trouble, can go to another guy's dorm room or invite somebody else to come over. That's harder for a woman to do, and if there are very few women, it's really hard. And so that's an example of the sort of thing that she saw as missing and she made possible. But I won't go into that, except to say that what's missing is that all of the speakers here are men. None of them are women. And this really needs to change. And I was talking with Lenore about how it could be changed. Lenore has some ideas, and my only idea is that there are some really great women who should be brought by, who could give a really wonderful talk. There's a woman, Ann Condon, somewhere in California, who has done outstanding work. She has never been recognized really for the great work she's done. She'd be a wonderful person to bring here. Another one is Moore Harcourt-Balter, is a wonderful woman, and she gives outstanding talks. She is very exciting. She gets huge audiences. She really should be here. She would be a great role model, and she'd do a great job. So what I find missing is the women to inspire the women.
What do you hope happens in 5 years? What do you hope that the students that you're meeting here will accomplish in your field?
5 years, that's good. So I'll tell you something else which I believe in, but very few people would. When I got started, because Marvin Minsky was my advisor, I really got into artificial intelligence. I really liked the idea. And I remember talking to other computer scientists about machines playing checkers. Machines will never play checkers, but then of course they did. In fact, checkers was understood mathematically perfectly, solved. Well, okay, checkers. So I remember talking to Dick Karp, wonderful computer scientist. Well, next machines will do chess. I said, oh no. It's very hard to even be an expert. Maybe they'll get to the expert level, but they will certainly never get beyond that to the master's level. This requires thinking. So I became expert 2, expert 1, masters. They became masters, and in fact, they eventually became world champion. So computers did do. I remember again the same talk. Okay, well, they did chess. They did chess, but they'll never be able to do Go. And so, and then AlphaGo, of course, beats the world champions at Go. So I have this question which I ask the students, which is, what do you think is going to be the next problem that everyone will say, okay, maybe the machines did Go, but they cannot do this. What will be that next problem? It should be kind of like a game where it's very well defined and where it's clear whether the success has been achieved or not. And people have suggested different things, like along the lines of Jeopardy, or, obviously if a machine can generate the questions for producing given answers, they can also generate answers to produce for the given question. So, they're talking about stuff like that. Now, I know we can build a machine to answer questions. What is it that so the point is, so I have a suggestion for what it is that people will generally say, no, machine cannot do that. And I would say that take any field of mathematics to become the world's expert in that field, the world's greatest algebraic geometer, to solve these really hard problems in computer science or in analysis or this. I think most people even here would say, well, whatever machines can do, they will not be able to do mathematics. And I'm absolutely convinced that within 10 years at least, machines will be great at mathematics. They will be world champion level at mathematics. And for a good reason. It's very important to read mathematics. Machines can read them much faster than I can put the stuff together. I need to work with other people because I have what I know and other people have their ideas from their fields of knowledge. A machine can read all the books and bring the stuff together. Machines have enormous advantage there. And I have a pretty good idea how the machine could, in fact, then do the mathematics. That it's not amazing, it's not magic. And it's going to start with this talk I give on consciousness, but I'm hoping that these students, at least some of them, will be the ones that eventually get the machine to be the world's greatest mathematician.
I wish we could continue this conversation. I think Fred Brooks is standing outside and nodding and wondering. Thank you so much.